Okay, welcome everyone to this workshop on Spatial Data Fundamentals in R. Thank you for coming for this Friday afternoon. I'm Andy Lyons, and I'll be teaching this workshop today for the next couple hours. And I'm real pleased to be here with everyone and excited to talk about this topic because uh, R is really good for working with spatial data, and it's something I've been working with for a while. So I'm looking forward to this. So I'll put a link here in the chat window to our workshop materials for those of you who just came in. You don't really need this, but you're certainly welcome to. These slides and the exercises will be online for quite a while. I will talk about how you can download them um, for a copy for yourself. But let me just go ahead and jump right into our slides for today and get going here. We'll do a little intros. So, first of all, a little bit about me. Many of you have attended the data wrangling workshops 2 or 3 weeks ago. So this will be review. So, but I'm working with the UC Division Ag and Natural Resources, as are most of you. And this is a part of the UC system. If you're not familiar with this, that is very applied, and we have academics across the state of California, mostly living in communities off the campuses, researchers who are doing research and extension in agriculture, natural resources, resource management, nutrition, a whole bunch of interesting, important areas. We have clusters of faculty on roughly 5 of the 10 UC stations, UC campuses, and a bunch of field stations. I work for the Informatics and GIS group. We are one of roughly 14 now, statewide programs and institutes. And this is a little bit more about me and my team. So you can see us here, and there's a couple of us here. We are basically a GIS shop, and we have the mission and the privilege to providing all manner of GIS support to this entire network of people who are working in ag and natural resources. We do all manner of GIS projects, from making maps, from chugging through spatial data. We have research drones that we fly for research purposes. We make mobile apps. GIS is becoming a lot, is becoming much more blurry now. So we do a lot of web projects as well. We teach workshops like this one. A good way to grab us is through office hours. We have office hours Monday and Tuesday afternoon. So please sign up for office hours. Google it, you'll find us. It's a great way to talk to us about any topics that we're familiar with. And you can see some of them here, but pretty much anything dealing with spatial data, spatial technologies, data science, and so forth. I want to give a special shout out to my comrade here. Genoa is with us, who
Hello.
backed me up. And yeah, you want to say hi, Genoa?
Sure. Hi, I'm Genoa. I work with Andy in Informatics and GIS, and I have a background in natural resources management, range management, and forestry. So always thinking about the scale of data you're working with, how you can be more efficient about it, and kind of how it can be applied for the betterment of people and the environment.
Well said. Well said. Yeah, so we're here for you, and so please feel free to reach out if you want to chat about any of this for follow-ups. I mean, obviously, we're not going to cover a tremendous amount in 2 hours, but we are here to follow up. So here are some of the other workshops we have running this semester. So we have 3 more to go. So next week we're going to have a webinar introducing people to ArcGIS Hub, which is a nice platform for making websites and data portals for teams and projects. Then we'll have another webinar in a couple weeks on making maps without GIS, which I'm looking forward to, and then Cordo, which is another R topic, R and Python. It's a reporting engine, which we'll actually be seeing today. So yeah, so you feel free to come to our training pages to get to sign up for these or to look at the recordings, which are also on our YouTube channel. A little bit more about myself. So I do work with R quite a bit, and these are some of my packages that I've developed. over the years. So I won't go into much detail here, but Degree Day, this is a package that computes agroclimate metrics, which are useful in predicting plant and insect development. UAS-IMG, that's for managing your drone data, which using drones for research does result in a whole bunch of data. This kind of helps you create catalogs and manage it, some utilities. CalAdaptR is an API wrapper, so it allows you to bring climate data into the R environment through an API, so you don't have to download ginormous TIFF or netcdf files. And then TLOCO is another one that I did during my grad work that computes home range constructions and spatiotemporal analysis for wildlife tracking data. And then more recently, I've been building a lot of Shiny apps, which are kind of like these lightweight web apps that you can use building R, which is pretty cool. So a little bit about the people who registered for the workshop here. This is a map that I generated with R, obviously. And there, I'll put the link here to the, if you're curious, there's a link here to the code that I used to make this leaflet map. I'll put that here in the chat window here in a second. But yeah, this was done with R, right? So we're not going to talk about geocoding today. We don't have time for that, but obviously you can use R to geocode. Of course, you need an online service to connect to, but there's several of those. And this is a nice little lightweight leaflet map. So just put we see the usual suspects. We always get a bunch of folks attending our workshops from the Berkeley and the Davis and this region of California. But nice to see also a number of folks registered from SoCal and even some overseas folks. So this is just an example of some of the cool stuff that you can do with spatial data in R. So let's talk a little bit about our goals for today. So really, the word fundamentals is part of the workshop title, and that's really kind of my hope here is that you will get a better understanding of the fundamentals of working with spatial data in R. And I'll explain a little bit more about what I mean by that and why. But just kind of understand how it all works, not just throwing together code that somehow works. You should definitely get a good sense of what are the go-to packages for working with spatial data in R, especially vector data, which will be our focus today. The recipes that, or the exercises that we're going to be doing are in these notebooks, Corda notebooks. So they're designed to, when you're done with the exercise, to render it to HTML, and you get these nicely formatted HTML documents that you can keep for yourself and use as your own personal library. So a lot of people who, develop code recipes, libraries of working code that they can return to as a good way to learn something like R. So no matter where you are in your learning curve, hopefully you'll learn, even if you're pretty advanced, you'll learn one or two tips or tricks today and come out a little bit higher on the learning curve. But I think it's probably clear that, in 2 hours, we really can't cover a whole lot. And to learn something like a programming languages, you really do need to keep practicing, right? So just consider this as the beginning, and I'm more than happy to work with people on specific projects. But programming is something you have to do. I feel it's kind of like swimming, right? You can't really learn how to swim very well by reading a book or attending a workshop. You have to kind of get in the water and keep exercising your muscles. One of the reasons I'm hoping to really focus on some of the fundamentals is that if you're a little higher up on the learning curve, it will allow you, in my opinion, to make better use of the phenomenal resources that are available on working with spatial data in R. And there's lots and lots of those, right? So geocomputation with R. This is an ebook. There's also a print copy if you want, but this is kind of my go-to. It's been written and developed and maintained by some really smart people who've written the packages that we're using today, and it's well divided up and has lots and lots of good examples, right? So when I have a question or don't understand something, I usually turn to this ebook. First, there's a version of this for Python as well, for those of you who also use Python. The Gen AI engines, I find them pretty good. If you ask it a well-defined question, kind of use it as a good search engine that's more conversational, they're actually relatively decent, certainly for the simple questions. Um, so understanding the fundamentals will help you ask good questions and kind of evaluate the results. So you're not just kind of like taking them at face value. And there's lots and lots of other great resources for working with spatial data in R. There's entire books. Lots of instructors have entire classes online, lots of blog posts, lots of YouTube videos, lots of forums. So understanding the essence of how these functions work, the terminology, I hope will give you a leg up so you can make better use of these kinds of resources. Okay, so what are we going to do in part one today? We're going to first look at I won't go through it in depth because we're going to go through this, but looking at why would you want to use R and GIS together? Like, how does that make sense? We'll talk about our spatial ecosystem. Then we're going to do a deep dive into the SF package and look at the data classes from the SF package, because that is kind of the mothership of working with vector spatial data in R. We'll see some functions for importing vector data, managing the projections, doing attribute queries, or which is another way of saying subsetting features and selecting columns. Very basic visualization with ggplot, and then we'll go into an exercise. Okay, so feel free to interrupt me as we go on if something comes up. Otherwise, I will check the chat window as I can. Yeah, so let's talk a little bit about why would you even want to work with spatial data in R? Like we have all these GIS programs. Why don't we just do that? Well, one thing I think it's good to remember is that GIS is not a simple, no longer one thing. Like maybe 20 years ago, it was just, an ArcGIS program or QGIS. But now it's really divided. There's all these tools. Some of them are command line, some of them have interfaces, some of them are only managing the data. Some of those are really much more visual. So it's not a single thing now. So the more tools you have in your toolbox, the better off you're going to be. And this is, I have a tech note. I won't put the link in here, but I wrote a tech note a couple years back on some things to think about when you think about which of these platforms and tools would make sense for my specific project. But there's a lot of stuff out there right now. It's not just one thing. And a lot of people want to gravitate towards, is R better than Python? Is R better than QGIS? I don't think this kind of either or is really a helpful way to think about what your options are. I mean, obviously, you only have so many hours in the day and only so much mental bandwidth. So, you do have to make decisions. But a better kind of question is how to combine programming languages like R with your desktop and cloud GIS platforms. All right. So with that kind of question, some roles that I think R can play is it can be used as a replacement for some GIS tasks. And I think as you'll see today, really that's where working with the data is central. So, R is fundamentally a data science language, and it's really good at creating data, munging data, joining data, wrangling data. So those kinds of tasks R can do really, really well, including automation. Automating workflows, right? So here's another example where again I wrote a little tech note about this process I had to go through. I was doing it, through clicking through a ArcGIS Pro with it just became a pain. So I put a little effort and figured out how to do the same workflow in R, and because it's something I had to do multiple times. So automating workflows is something good programming languages are really good at. A lot of spatial analysis is developed by researchers who do their work in R. So there's a lot of platforms. So Forest Tools is one R package that was developed by some forestry researchers. So there's all these metrics and analyses that are kind of tailored towards forestry. And there's lots of good examples of that, right? So The desktop GIS programs will also bring in new spatial statistic methods, but it's usually going to take them much longer to do that. So there's some spatial analysis tools and methods and algorithms that really might only be available in R because researchers use it a lot, especially in ecology. There's a lot of similarly, there's a lot of data and services that you can get online, and the API clients often come out first and in open source languages, and are very well equipped to work with online data. And I like this graphic because R, once you get comfortable with it, it's very good for working with the data, for accessing services, for bringing in other stuff. So using it as kind of a command and control center um, is another way to think about how R might complement your other GIS resources. Where R, I would say, shines is definitely spatial statistics, right? R was first and foremost developed by statisticians and data scientists. So pretty much every spatial statistic method that's out there is likely to be in R. So that's clearly a strong suit of it. It's based on its roots and its community, including statisticians. They are dominantly or mostly using R. Most statisticians. It has a fantastic reporting engine. R Markdown and now Cordo. These slides are made with R Markdown from R. You can make websites and notebooks. We'll be using it today. Cordo is now cross-platform, so Python users can use Cordo as well, and it really is a really great reporting engine. So come to our webinar in December if you want to find out more about that. Shiny, also cross-platform now, so it's not unique to R, but Shiny is a really nice package extension that you can use to create lightweight Shiny apps, lightweight web apps, or heavy web apps, right? That are based on our code, right? It dramatically lowers the bar of what you need to know to get your R code onto a website that other people can use. Using R as a development platform, it's well equipped for that. You can really drill down into the weeds. It has a fantastic system and set of protocols and platforms for sharing your code as packages, your data as packages. It's well developed, it's robust. R Universe is out there now. There's also GitHub. So if you're willing to spend a little bit of time to learn how to bundle up your work and because you want to share it, R is a good choice for that. That was the main reason I started using R, actually. My advisor in grad school said, if you want people to cite your paper, you need to make it easy for them to access your work, to use your methods. And yeah, I realized he was right. Kind of extended my grad program a bit, but I'm glad I did it because my home range paper is now heavily cited, and I think it's primarily because it's backed up by an R package. You can use R for anything that's kind of out of the box, right? Which is a big reason people turn to it because they get frustrated with what's limited in a desktop GIS program. So anything which is new or a little different, generating data from scratch is another strong suit. All right. So in terms of some of the tools you have to integrate R and your other GIS tools out there, because it's not a panacea, it's not going to do everything. ArcGIS is a well-developed ecosystem of data and online services and desktop software. So there's a couple R packages that are available to help you work with that. The R ArcGIS Bridge is the order of these, and basically it's a package that you can use to get data in and out of a file geodatabase if you're working with the desktop GIS, ArcGIS Pro. So that's handy. Uh, but there's also in the last few years, there's been a series of other additional R packages that have been developed that give you access to ArcGIS online resources, which I think is really exciting because there's a lot of that, and we're going to actually use this today. to download some data because many agencies and organizations are sharing their data through the ArcGIS ecosystem online. So we're going to see some of those. If you are a QGIS user, you can use R. You can use a plugin to kind of give people in QGIS access to your R work. That's another role of the R ArcGIS bridge. That's more for pro developers than for R developers. And then there's a bunch of other stuff that you can use if you want to bring into R other kinds of data or services from the cloud. The SF package supports URLs, and we'll see some more of these ones. So there are some options there for integrating R in your desktop GIS tools. People always are curious about like R versus Python. They play well together. So you can, in R notebooks, you can run Python code and vice versa. The engines are becoming increasingly cross-platform. I would say we're some areas where Python really shines in this what we're talking about here. The ArcGIS ecosystem is really based on Python, whether that's Pro or the cloud services. So if you want to write scripts to work in Pro or to control Pro or online or do some of the administrative stuff, Esri has well-developed Python libraries for that. And then many of the kind of the new AI models for image analysis and deep learning are being developed by industry in Python. And many of these are available in R too, but they might take a little bit longer there. And it depends on who develops them. All right, so let me pause there. And does anyone have any comments, thoughts? Want to add something else about how R and GIS can work together? All right, well, feel free to throw things into chat if ideas come up. Okay, let's talk a little bit about R's spatial ecosystem. So the essence of R is this ecosystem of packages, right? So packages give you functions that expand what you can do in R from the base installation. So there's a bunch of them out there, but probably SF is going to be the package that you'll most likely be using, certainly if you're working with vector spatial data. So this is kind of the foundation. And what it provides are going to be those core spatial data classes. It's got import, export routines. Most of the geoprocessing functions that you might need, like the buffers and the clips and the intersections. It has some enhanced plotting, but there's other packages that do that. It helps you manage your projections, spatial joins and queries, overlays, so on and so forth. So this is really kind of like the Swiss Army knife. This package, this SF package, has all of the nuts and bolts that you can do for preparing your data, getting it ready for something else. In the raster world, Terra is probably fills that role now. That's kind of the successor to the older raster package. And if you're working with spatial temporal data, there's a stars package, which is also pretty central for those kinds of data. Right. So I would say these three packages are probably the core, the foundational packages. There are others that you might need to use. But then there's a bunch of specialized packages here. So for example, if you're doing spatial stats, you might use one of these packages. Now, I don't do a whole lot of spatial stats, so I don't have enough experience to talk about the pros and cons of these and what you might use for each ones. I kind of do it as needed, and then I forget it because I don't do it enough. Likewise, for network analysis, there's different kinds of methods that you can use for those kinds of data, different ways to store those data. In the visualization area, that's a fairly well-developed set of packages there. These are some of them. I've used most of these. Today, we're going to be just focusing on ggplot because it does the basics. And that's all we're not kind of focusing on visualization in this workshop. But tmap's quite good. Leaflet is still, we saw that leaflet map before. Map view can also create online maps. Tmap can do both nice static and online maps. And there's some other ones. There's a couple of packages for geocoding And then this is just, my background's in ecology, so I know a couple of the ecology packages, but in any field, soil science, and they're not even putting the remote sensing packages on here. That's a whole nother universe. So lots of good packages though. It's a well-developed ecosystem, which is partly why it's been so popular. All right. Feel free to throw in the chat window if you are looking for, what package you might use for a certain kind of use case, or you know something else. Okay, but let's turn to the SF package because this is quite central. It's primarily working with vector spatial data, right? So points, lines, and polygons. Uh, it's based on an open geospatial consortium standard. So it's based on a well-developed, discussed, and developed over a couple decades, a way of storing various spatial geometric data in a tabular format, right? That's called the simple feature format. And here it's, feature just means that thing on the ground that you're trying to represent. Some of the reasons people like the SF package and why it is really come to dominate, and many other package developers have adopted it as kind of uh, being compatible with its data. It has, again, I mentioned all of the features that you would want to read, write, create, edit, and manipulate GIS data or spatial data. It leverages other really well-developed open source projects, again, that are 2 or 3 decades old. GDAL, GEOS, and Proj. GDAL is your import-output routines. GEOS, it's all these geoprocessing functions, and then Proj it handles it's like the massive catalog of all your coordinate reference systems. SF is fast. It provides some better plotting, and because of these reasons, many other R package developers have adopted it as the standard for spatial data that whatever their package is bringing to the table knows how to use. Okay, so SF is pretty popular. A little bit more drilling down into how it encodes geometry. So basically, it's, simple feature. As I mentioned, it's a data frame that has a geometry column tacked onto it, right? And that geometry column is like all good GIS formats or spatial data standards. It can support points, lines, and polygons, and multi-points, multi-lines, and multi-polygons. So all your kind of standard shapes or geometric types. It can even save in a single table. It can mix and match the features or feature types in a single table, right? So you can have a layer which has some points and has some polygons and lines, which you don't see that in the GIS world. Um, and I've not actually had a project where I've needed or wanted to use it. Kind of like it's a bit of a mind bender to think about a use case, but I'm still always looking for an example where that might be handy. If anybody knows of a use case where it would be good to have a layer that has different kinds of geometries all together, yeah, feel free to chime in or type something out. But the
Well,
magic,
Andy, I have an
yeah.
example.
Oh yeah, go ahead. No.
I've been doing network data of these points, and the lines represent the um, distance between certain it's like schools and vendors, right? And then producers. And so often I'm trying to relate the point information to different lines and then also to distances at the same time. So being able to create and store each unique combination of points with both the relevant points as geometry columns and then also the relevant line geometries is much simpler than having multiple data frames until I have to write to file
Oh, okay, interesting.
for me because
Oh,
I'm still doing a lot of statistics at the same time.
so do you have multiple geometry columns in a single table, or do you have a table with one geometry column but with different types of features in it?
I have a table with 6 geometry columns.
Okay, that's
Oh, but you're talking about mixed in the same column. I see. We did
Yeah,
do that
well,
once for cases where you do have centroid geometry for some data and polygon for others, and you want to be able to use it as a spatial reference, but you just don't have polygon data. So it's representative geometry mixed
yes,
with
yes,
literal.
yes. Yeah, yeah. Yeah, yeah, and what you mentioned is another capability it has, right? So you can have multiple geometries in a single table, and yours
Yes.
is a good use case.
Sorry to interrupt.
Somebody, yeah, somebody asked, does R handle support polygon topology? And that's a good question. You don't have to like manually construct your topology the way we used to have to back in the day. And I don't know. I do know that you can have polygon layers that have problems, like slivers and that kind of stuff. That comes up occasionally. So I don't, that's a good question. I don't know. And I know there's other packages that are designed to help you deal with topology issues. But big, yeah, so that's a good question. I'm gonna take note of that and maybe um, uh, think about that. Um, yeah, topology is not something though that we have to kind of worry about, at least not in the kind of work that I do. But that geometry column, it's basically a text column, and it uses a standard called well-known text. And this is just a way that you can encode points, multi-points, lines, polygons, and so forth. And you can act, sometimes you see this, right? A lot of times you don't see it, you don't want to see it, don't need to see it. But that geometry column, it's basically a text column, and this is what it contains, right? So yeah, so basically it's a data frame plus that geometry column. And then the other piece, the other thing that's in a simple feature data frame object is the spatial metadata, right? So the bounding box, the coordinate reference system, and so on and so forth, right? Okay, so here's a real quick example of working with a SF object. So we load the SF package, and then that particular package has a shapefile, so we can read that. And as you see, when you look at the class of it, it is an SF object or the SF class, but it's also a data frame. So what that means though, is that if you have a simple feature object, whether it's lines, points, polygons, it is fundamentally a data frame. So any other function that you can use on data frames works on these SF objects, which is fantastic, right? Because R is really good at manipulating tabular data. There's lots and lots of functions, especially from the tidyverse, that are designed to work on data frames, and those work out of the box with the SF package or data classes from SF. And we're actually going to use some of that. So for example, head, right? Head is a function that works on data frames. It shows you the first 6 rows, which in this case are features. And when we use that, you can see the results. The first bit of it is the metadata, right? The spatial metadata, the geometry type, the bounding box, and the coordinate reference system. And then we see the columns, right? Same way we would, and that there at the end, you can see the geometry column. Okay. And then you can also plot that geometry column by just grabbing it with the $ and using it in plot. And that's the good way to make a quick and dirty plot of simple feature data. In the exercise, we're going to be using ggplot, but this works as well. Okay, questions? All right. As you've already seen, a lot of the functions from the SF package start with ST, so that's helpful. Many of them take pipes or are pipe friendly, meaning they want to receive as the first argument a simple feature data frame, and they return a simple feature data frame. So you can kind of chain them together with these pipes. And there's, I'm a big fan of cheat sheets. I will put this link in the chat window here. That first link is the code that generated that leaflet map, and the second link there, if you are curious about the cheat sheet for the SF package, because there's a lot of functions here and you might guess them, but you might not. So that can help you get started. But let's talk about importing spatial data, because that's probably something you're going to do if you're working with spatial data in R. is you got to get it in. So not hard to do. When you're importing spatial data into R with this SF package, there's two things you have to know. You have to know the source and you have to know the layer, potentially have to know the layer, right? And you're going to feed these into one of those functions. So the source, it depends what you're bringing in, right? If you're bringing in a file format, like shape files, the source will be the folder where those files live, right? If you're bringing in data from a geodatabase, so geodatabases, if you look at your Windows Explorer, it's actually a directory or a folder. So in that case, the source is that folder. So the folders for a geodatabase normally end with .gdb. So you construct a path to the folder. If you're bringing in from, say, a KML file or a GeoJSON file, then the source is that file, and then inside those files could be one or more layers. The source could also be a database connection string, which we're not talking about here, but that could be like if you're accessing a database. The layer is the second argument that you're going to need to know, and that's simply going to be the name of the layer, right? Which sometimes that's the same as the name of the shapefile, but in these other formats, you might not, you might not be able to just kind of look at the file and know what the layers are there, right? So if you have a source, say it's a file geodatabase, but you don't know what's in there, you can't open up Explorer and look at it. It's just a lot of weird um, SQL files. The st layers function will tell you the layers in a source, which again could be a KML file, GeoJSON file, database. And then once you got that down, then you can use the stread function to actually, that's what you use to bring it into R. All right, you provide the source and then the layer. The source is the first argument, but if the named argument is actually DSN. Okay, questions? All right, so bringing in, as you probably gathered, the SF package supports like dozens of file formats. It knows how, because it's using GDAL, I think, on the back end. So it knows how to use, it knows how to bring in data from many, many formats. Let's talk a little bit about projections, because this is something you have to pay a little bit more attention to. You can get away with not knowing much about projections for a lot of desktop GIS because they handle it on the fly on your behalf. But it is more important to be aware of and manage your projections when you're working in a programming context. So projections is simply the math that we use to take coordinates on a round planet and put them onto a 2D surface. The more general term, which is what I will be trying to use henceforth, is coordinate reference system, which includes projection systems, but it also includes latitude, longitude coordinate. There's thousands of them out there. If you've used any kind of GIS software, you've probably seen this. The good news, though, is that there's a catalog called EPSG that has kind of gone viral and everybody uses. And you can look up for any coordinate reference system out there, you can find an ID number. So all you need to know is the ID numbers. And you just kind of keep a hold of those. So this is important in plotting. So in desktop GIS, you can mix and match layers in different coordinate reference systems, and the software will project them on the fly on your behalf so they line up nicely. You may or may not get that in R. Many of these R packages do not do that. ggplot, which is what we're using today, will actually reproject on the fly on your behalf. So we're going to be we don't have to be super rigid on this today, but it's good to have all of your layers in the coordinate reference system, in the same coordinate reference system, so that you know how they're being added together. Right? You're not letting some programmer make those decisions for you. But if you are going to compute geometric measurements like distance or area, that's really important that you're using units, a projection system that uses real world units like meters or feet. Otherwise, the results can be hard to interpret and vary depending where you are on the Earth. If you're near the equator or near the poles, And then also, if you are going to do spatial queries for spatial joins, CRSs are important there as well. You'll actually get an error if you try to do a spatial query or spatial join with two layers that have different CRSs. So, but fortunately, the SF package has a good set of functions. If you just want to see what is the coordinate reference system of an object that you have, you can use st_crs. If you are reading data from a GIS file format or database or writing to one, they will import the CRS info and export it, so you don't have to worry about it. And then if you do need to transform or reproject from one CRS to another, you can use the st transform function, right? So this stuff's pretty easy. You just have to remember how to do it, or that you need to do it. Most people use like maybe a dozen or less EPSGs. In my world, these are the ones that I use the most. So I just came up with I just keep this little code snippet in my notepad, and then these are the coordinate reference systems for California that I encounter mostly. So I would suggest you come up something like this. This little PDF here from CDFW has a nice little explanation of the coordinate reference systems that we find in California. I don't use state plane very much, thank God, but that's another set of coordinate reference systems out there. Okay, so we've talked about importing data. We've talked about managing projections. Another way that you can import data is from cloud services, and increasingly in our world, there's a lot of data that's on the cloud. And of course, you can go to some website and download a zip file and unzip it, and it's a big TIFF file or maybe a zipped up geo database. But many agencies that we work with are sharing their data online through the ArcGIS ecosystem, for better or worse. That's the dominant platform. So this ArcGIS layers package by a really talented developer, Josiah Perry, who works at Esri. He's put together these various a set of packages that you can use to interact with online resources from ArcGIS. So yeah, this is really useful because there's a lot of agencies that are using that platform, including ArcGIS Online, as well as their like on-premise ArcGIS Enterprise portal. A really nice thing about these packages is you don't need Pro, and that's good news for Mac users because installing Pro on Macs is kind of not really very viable. Another nice thing about this package for downloading data from as resources is if a lot of times cloud data, it's much more than you actually need. Like you just need watersheds for your county, but the only layer out there has them for the entire state or the entire country. So you can do the functions in this package allow you to pass attribute filters or spatial filters, right? And the key thing is that those filters are done on the server. So it's not going to send you, a gigabyte's worth of data and then filter it down to just your area. It's actually going to do that filtering on the server, all right? So basically, yeah, we'll go through this workflow here coming up. But basically, to import data from an ArcGIS source, you have to basically get a URL, right? So you look it up, or you Google it, or you stumble across it from a data portal. And specifically, you're looking for the URL for that feature server or the map server, right? We'll see an example of that. And once you got that, you're good to go. You feed it into a series of functions, you select the layer you want, and you bring it in. All right. So we'll see some examples of that. Okay, I'm going to go through this, past this one, because we'll see this here coming up. Actually, I'll talk through it real quick. So basically, here we have an example where we're importing a public layer from an ArcGIS website. And the first thing we do is we grab the feature service URL, and you'll know it's a feature service URL because it ends with feature server, right? If there's a number after that, like 0-0-1, that's one of the layers inside the feature server. That'll work too. But once you get that URL, you feed it into ArcOpen from this ArcGIS layers package, and that creates a kind of like opens up, it's kind of like dialing it up on the phone, right? So now you have a communication channel going. And then many feature servers have one and only one layer, but others will have multiple layers. So you can see what layers are available on that feature service URL with the list items function. In this case, there's just one. And then to actually get that, to get the layer object, you can use the get layer function. But at this point, we still haven't brought anything in. We're just kind of like dialing, we're just identifying on the server what we're trying to get to. To actually bring it in, you use the arcselect function. And this is the function where you can add a filter. For example, this filter, it's an attribute filter, right? So there's a column in this layer called state FIPS, and we're passing this where expression, which is just telling us only give us the rows, the features where state FIPS equals 12, which is Florida. Okay. And we're going to see an example of a spatial filter coming up. Okay, so before we go to our exercise, do a quick review of ggplot, because this is the package that we're going to be using to make some maps, simple maps. So as you all know, ggplot is a widely popular package for plotting in R, and it follows the grammar of graphics. Here's an example of a ggplot statement, which generates a scatter plot, right? So let's dissect this a little bit more, and then we'll talk about how we can use ggplot to make maps. So this is that same ggplot expression, which threw up that map. So the first thing we notice here is that it's a series of functions from the ggplot package and other packages that are added together with the plus sign, right? So that's point number one. A ggplot expression is always going to be at least two functions that you've added together. Okay. The opening move is always going to be ggplot. This kind of like sets up a blank canvas, at least, or that's how I think about it. And then optionally sets up the data. So the thing about ggplot, and this is true for making maps with ggplot, is that all of the data that you need to make your layers, to draw the layers, have to be together in a data frame. All right. So if they're in separate data frames or they're in different vectors or something like that, you need to bring them together into a data frame, including a simple feature data frame. So that's the first argument that's usually passed. And then this AES function, this is where we tell it the defaults for what columns in that data frame to use for the x-axis, for the y-axis, for the color, that kind of idea, right? So this is setting up mappings between the visual properties of the things that we're going to be drawing here in a second with columns in the data. And then you have one or more of these geom functions. These are the functions that actually draw things on the canvas, right? So geom point is going to draw dots, and it's going to inherit whatever defaults that you set higher up in the ggplot statement. So, to make a point, you need an x coordinate, you need a y coordinate, you might need a color, or you can accept the defaults, but it's going to look in your mapping statement to see, how to make those points. And then there's a bunch of other functions that you can tack on at the end to kind of, the title, the legend, the axes, and so on and so forth, the theme. There's a bunch of these optional functions that you can use. Right? So we're basically going to be doing this with maps as well. But with the maps, we are going to be using, I'm gonna go through these, a couple of those slides. With maps, it's basically going to be the same. We're going to use ggplot. We're going to feed it our simple feature object, but then the functions we use to draw the layers are going to be geom SF, right? Assuming that we're feeding it an SF object, we're going to use geom SF as the geom function because it knows how to read simple feature objects. And that's really it. Something else which is a little bit different between regular plots and maps, like maps tend to be multiple layers. So you're probably going to have multiple geom SF. And unlike other plots, probably every GeoMSF function is going to be using or drawing upon a different simple feature object, right? Your roads and your administrative boundaries. They're probably all going to be saved in different simple feature objects. So what we do there is we generally put the data object, the data frame, inside these GMSF functions and not the opening ggplot. Okay. But just like making maps in desktop GIS software, order matters. It's gonna draw them from the bottom up. And then there's ggspatial. There's some other packages that you can use that we'll see examples of to add other things to your map. The great thing about GeoMS, this is probably my favorite geom function out there, because it knows how to, it knows whether it needs to draw points, lines, or polygons, right? So if it's a point layer, it'll draw points. If it's a polygon layer, it'll draw polygons. So that's a really nice feature. You don't have to like tell it that, it'll figure it out. And then these are the aesthetic properties that you can either hard code, like if you want everything to be red, you say filled equals to red, and then all the polygons will be red. Or you can map these aesthetic properties to columns in your data, right? So these are the ones that you would typically use for making for symbolizing vector data. Okay. And here's an example of a ggplot. So again, we have this simple feature object that comes with the SF package. And here you can see, so in our ggplot, we don't put anything there. We still need it because we still need to initialize the map and kind of start a blank canvas. But then we actually draw something using the geom_sf function. And here you can see that the first argument we're putting in here is data. And this is an example where you do need to, most of the time you're going to use the argument name to tell it that it's the data, because there's lots and lots of arguments in this function. But the one we're giving the data has to be named. And then the second argument is where we're basically using again that AES function and telling it get the fill color from this column in the simple feature data frame. All right, so we basically get like a little kind of Choropleth map. All right, so that's just a simple example. As you might imagine, lots and lots of people have used this and come up with ways to make beautiful maps. So there's a resource here that you can turn to for more info. Okay, any questions? All right, before we jump into the break, I've been talking for almost an hour. This feels like a good time to take a 5-minute bio break, and then we'll jump into the exercise when we get back. So I apologize that the first hour-ish was a talking head presentation, but basically everything I've covered we will be using in our exercise. So you shouldn't be baffled or see anything in the exercise that we haven't already mentioned. So let's take a 5-minute break. We'll start it up at 2 o'clock and we'll go into our exercise. And I will stay on if anyone has anything they'd like to chat about or has questions on anything covered so far. All right, so I'll do that one more time here and then we'll get going. So again, I'm assuming most of you are going to be on Posit Cloud today. So click on the Posit Cloud link I put in the chat. And I'm going to do the same thing right here. So I'm going to open up a new tab in my browser. Stick that in. And it's going to basically make a copy of this RStudio project in your Posit Cloud workspace. And the first thing you should do after it opens, which takes a minute or so, is to click the Save a Permanent Copy button up at the top. And the good thing, though, is that the copy that you save after you've saved it, that will stay in your RStudio or in your Posit Cloud workspace until you delete it, right? So you can come back to it later if you like. All right, so I'm gonna do that. Okay, so somebody give me a thumbs up if you've been successful in opening up this project in Posit Cloud. Right, so if you're just coming back from break, click on the link in the chat window to a Posit Cloud or Studio project. And once it opens up in Posit Cloud, click the Save a Permanent Copy. And then the first thing you can do is there's not a lot in this project. Mostly it's exercises. So click on the exercises folder and then click on exercise 1.qmd. All right. So click on exercise 1. So in the files pane, find your way to the exercises folder, click on there, and then click on exercise 1 import plot QMD. So this is a Quarto markdown document, right? So if you haven't used Quarto before, now you have. We'll talk a little bit more about why I like Quarto. But basically, it's like any kind of markdown document, right? So I'm going to go ahead and close my console or minimize it because in a Quarto markdown document, when you run the code that's in these code chunks, these gray squares, if there's output from that code, like a plot or something like that, it's going to appear underneath the code chunk inside that Quarto markdown document. So it's going to appear inline. And then when we're all done here, we're going to render this to an HTML file. And that's the HTML file that you can keep for your library. All right, I'm going to keep going here, so feel free to chime in if you're stuck or something. So the first bit, so I'm working in this Quarto markdown document in the source editing mode. You can go to visual mode. Visual mode mostly works, but it doesn't completely work. So I've encountered challenges with the visual mode. So I'm going to stay here in the source editing mode. In terms of the HTML output that it's going to spit out when we're done here, that doesn't matter what mode you're in, right? Okay, so come down to code chunk number 1. So scroll down to about line 20, click anywhere in that gray box, and then click the little green arrow to run all of the lines in all of the commands in that first code chunk. Okay. So nothing happens. That's good because it means, we're not creating any output here. We got message equals false to get rid of that output. And then if you didn't get an error message, then it should have worked. Okay, next, come down to code chunk number 2. So come down at about line 32 and run that. And let's look at what we're doing here. So in this code chunk number 2, we're using the stlayers function, which again from the SF package. And that here function, that's simply constructing a path to a folder, rooted from the root of the project. So it's just kind of a pretty safe way to construct paths to files and folders. And what we see here is going to be all of the GIS layers that it detects inside that data folder, right? So you'll see in the exercises folder, there's a subfolder called data, and it looks like there's 6 layers that it detects. And yeah, so we see the geometry, we see how many features it has, which is kind of nice. And we see the CRS. So this stlayers function, it's pretty handy, right? Because even before we bring this data in, we know, oh, this is going to be UTM. Oh, this is going to be NAD 83 geographic coordinates, right? So, and these all happen to be shape files, right? So that's good. So scroll further down. And now in code chunk number 3, we're going to bring in the boundary of Yosemite National Park, right? So go ahead and run code chunk number 3. We're saving that as a simple feature object to an object called yoc_bnd_ll, which stands for lat long. And you can see the output when we run the stread command. It brings it in, and we get kind of a little preview of what it's doing. So now we have a simple feature object that's loaded in memory. You'll see the boundary of Yossi. So code chunk number 4, if you click down there and run that, you'll see I'm skipping through some of the text that's been written, which again, when you save this to HTML when you're done and go back through it, there'll be some more tips and information. But we're just going through the code right now, just for time. In code chunk number 4, again, we're looking at the class of that simple feature object that we just created. And again, it has two classes. It's an SF object. It's also a data frame object. Okay, so in code chunk number 5, come down to code chunk number 5 and run that line. We're basically just printing, as we do with any object, you run it by itself and we see a summary of it. And again, we see this, it's a simple feature data frame, simple feature collection, and we see a little bit of the information about it. So let's now plot this, right? So just to see what we have. So in code chunk number 6, go ahead and run code chunk number 6. And again, we're using that ggplot followed up by geomsf, and we're feeding in our park boundary. So we have a nice little map of the park boundary of Yosemite. Okay. Okay, so code chunk number 7 is a challenge. So we're going to pause here for a couple minutes, and I'm going to ask you to import the historic points shapefile and plot it, right? So if you click inside the data folder, you will see there is a shapefile. We also saw it listed previously. Alphabetize these. And it should be called Yosi_historic points. Yep, so there's a shapefile. So your job is to import it and plot it, right? And you can use the commands that we just looked at, right? So let's everybody take a couple minutes to do that first challenge, code chunk number 7, to bring in the historic points and then to plot it. And if you want a little bit of a challenge, you can plot those historic points on top of the park boundary. Right? Okay, so I'll work through this also. So, Ooh, okay, thank you. All right, we have a couple folks there. All right, I'm going to copy paste Joanna's solution. Go through it. All right, I'm just going to run through this. And yes, this looks beautiful, right? So again, we can use the stread function, basically just kind of copy paste what we use to import the park boundary and change the name of the layer, right? Because that's the only thing that's different here. Save it to another object, and then to get the points overlaid on top of the park boundary, we can just add it to another geomsf function in our ggplot statement. So perfect. Okay, let's keep going. So next, let's go ahead and import the another shapefile, another point shapefile. And this one is the points of interest. So this is code chunk number 8. Go ahead and run all of code chunk number 8. And as you can see, we're importing it. It's a shapefile, points of interest, different points of interest. We'll look at some of them soon. The head function will show you the columns in the data. It's a little bit of a clunky display. So yeah, that's not very helpful. Actually, yeah, so you can see there's picnic areas and there's, they've got labels. So this looks like it's probably exported from an Esri product. That's usually pretty high feature ID. That's definitely going to be an Esri product. Anyway, but it plots really nice. It comes in nicely. And in this ggplot expression that's plotting the points of interest and the park boundary together, you'll see some arguments that I'm using with the plot the park boundary. Fill equals NA. That's how you make a polygon layer transparent, right? So anything which is NA will be transparent. providing a custom color, so not accepting that default dark gray color as the outline. And then size is the thickness of the outline, right? I don't know what the default is, but it's one makes it a little bit thicker than the default. Okay, we have a nice little map there. Okay, next, let's so the points of interest, as you can see, there's a whole bunch of them. I didn't count them, but we could say, just to see how many there are, I'm going to say n row, right? Because that's going to tell us the number. There's 2,720 points of interest, so that's quite a bit. But there are different kinds of points of interest. So in the next bit, we're actually going to subset the points of interest layer, right? So if you click in code chunk number 9, in code chunk number 9, we are grabbing the POI type column from that simple feature layer. We're grabbing it using the $, the way you can grab column from any kind of data frame. And then we're feeding that into table, which will give us a frequency table of the unique values. And we can see the different, there's 1,200 campsites, there's 260 parking lots, and so on and so forth, right? So in code chunk number 10, we're going to use that information and we're going to plot just the parking lots, right? So go ahead and click in code chunk number 10, run the whole thing. And it's pretty intuitive, right? So the first thing we do in code chunk number 10 is we're using the filter function, which you might remember from our data wrangling workshop, is from dplyr. And we're pulling out just the parking lots and saving them as a new object. And let's see, how many are those? There's going to be 260 of those, 31 columns. We haven't gotten rid of any columns yet. And then we plot those. All right. So y'all just did that. We would call this in the GIS world an attribute query. An attribute query is where you're selecting features based on attribute values. So that's really easy to do, and you'll probably do that most of the time using either filter from dplyr or possibly square bracket notation if you're old school. Okay, any questions? Let's go to code chunk number 11. So click in code chunk number 11. To date, all we've been doing is importing shape files. But what we're doing in code chunk number 11 is we're going to import the roads, and the roads are not in the shape file. They're in a file geodatabase, which is also in that data folder. So in code chunk number 11, we're just creating an object that, the path to that directory. And then just verifying we typed it in correctly. So geodatabases, if you look at them in Windows Explorer or File Explorer, you can't tell what's in there, right? You need a driver to actually read the layers that are in there. So in code chunk number 12, run code chunk number 12. This is critical, right? We do need to use the stlayers function here to actually read what layers are available in this file geodatabase. In this particular one, there's only one layer. It's called Yosemite_roads. It's a multi-line layer, and we can see that it's in UTM zone 11 north. Okay, but now we know the name of the layer and we know the geodatabase, we can bring it in. So that's code chunk number 13, run code chunk number 13. We bring it in. It's pretty simple. We're saving it as a new object. You can tell by the information there that it is it's in UTM, right? So that's another, we see that at the bottom, that's the projected GRS. And then we can plot that in code chunk number 14, right? So it's just doing another plot. Yep, that looks like roads. And then, now this is something, those of you who are quite astute might have, does anybody notice anything funny about this plot that we just made of the roads? Anything that might be unexpected or not intuitive? Something's a little strange here. No bounds. Okay, right? So there's no park boundary, right? That's good observation. It's kind of even hard to tell if these roads are all within the park or somewhere else. We could overlay the park boundary. Yep, some of them aren't connected to anything, right? That's a good observation. They're probably cropped, unless they're like roads going to the top of a mountain or something like that. But something else which is curious here is if you look at the coordinates on the X and Y axes, we're seeing decimal degrees as latitude, longitude, but we know that this is UTM. And the coordinates of UTM data are meters. They're not decimal degrees. So this is a curiosity, this is a feature of ggplot that even though you're plotting UTM data, and if you're really astute, you see how like it's a little bit rotated. That's another sign that you're plotting projected data, the graticules. Um, but it's showing degrees, latitude, longitude. So that's what that little tip is down at the bottom. If you do want to see the real world coordinates, which in this case are meters, if you click on code chunk number 15 and run it, now we're seeing meters on the sides and it's no longer rotated, right? So now we're seeing it's plotting it, including the graticules and the tick, the label on the axes in UTM 11 north. And that's what that chord underscore SF, we kind of tack it on to our ggplot expression and it makes that change.
It is also interesting that when you force that shift, it also straightens out the grid lines because it's no longer using the decimal degrees.
Yeah, that's right. Yeah, that's interesting. Yeah. So projected systems, because got latitude, longitude is we have a round world. So when you're putting projected coordinates on decimal degrees, there's always going to be a little rotation. Unless maybe you're near the poles, I'm not sure about, or near the equator. But okay, so code chunk number 16 is a challenge to plot just the primary roads. So how are we doing on time? Not so good. Let's skip code chunk number. Let's skip that challenge so we keep going. We're gonna skip that next challenge, but there it's asking you to plot just the primary roads. So, we have a roads layer, but there's secondary roads, there's park roads, there's primary roads, there's parking lot roads, I think, there's service roads. There's a bunch of different kinds of roads. So you need to figure out how can you pull out just the primary roads and plot just those. All right, so that's that challenge. I'll let you work on that on your own because I want to get down to code chunk number 17, where this is where we're going to do something kind of cool. Actually, the first thing we need to do here is I'm gonna type in something here at the top of code chunk number 17 because I want you to see something. We didn't plot the roads against the park boundary. Let me come up here. I want to add the park boundary to our road layer. All right, so we can do that, and then I'm just gonna say geom. I'll put this in the chat window also. UCB and D LL. Oh, I need to make this. I'm putting it on top, so I need to say fill equals NA. Let me make it green also, so it stands out a little bit more. That would be color equals to dark green. I'll do this. Oop, didn't like that. All right, I'm gonna put this in chat window. We'll make it a little bit size equals to 3. Okay, so I put a expression in the chat window that you can copy paste. And basically what it does is it's displaying the roads and it's overlaying the park boundary. And obviously what you can see that's going on here is it's a little bit unfortunate that the road layer extends beyond the park quite a bit, actually. I'm not sure why. We'd have to go and read a little bit more about whoever published that road layer and what their criteria was. I guess they were interested in roads coming into the park, so it made sense. But suppose we're interested in something like how many miles of roads do we have so we can plan our maintenance and our budget, that kind of thing. So the next thing we want to do here is we want to only get the roads that are inside the park. So this is a spatial operation. This is an intersection, right? So what we're going to do in code chunk number 17 is do exactly that intersection. But we have a challenge, right? Because the roads are UTM, the park boundary is latitude, longitude. And we can get away with plotting these together because ggplot will do projection on the fly for you. But you can't get away with that for doing an intersection. You will get an error message. You can try it if you'd like. But what we need to do here, before we can intersect and pull out just the UTM, just the roads that fall within the park, is we need to get them into the same coordinate reference system. So what we're doing here in code chunk number 17, the first thing we're going to do is we're going to project the park boundary into UTM 11 north so they match. All right, so here we're using the ST transform function, and we're piping in the latitude longitude simple feature object, and then the next argument is stcrs, and I don't know the EPSG number for UTM 11 north. I could look it up, but we don't need to know it because we know that all we're trying to do is trying to match the road layer. So you can kind of extract the CRS from the road layer and use that in ST transform. And the result is now we have a version of the park boundary that we can use in the intersection function. So ST intersection is one of the geoprocessing functions. It does what it says. It'll return the intersection of the roads. And then in the next two lines are going to show us the original road layer has 823 features. And then after we do this intersection, we're getting only 638. So we would expect it to have gone down, and it seems like it did. And then finally, in code chunk number 17, we're plotting this subset of the roads against the park boundary. And indeed, they do fall within the park boundary at this point. Right? So again, we're using ST intersection as the kind of the predicate there for this. We're using intersection as the predicate for the ST intersection function. You can also do contains, and there's like 6 others, within certain distance, overlaps. There's a few other kind of spatial relationships that you can use in that ST intersections function. Okay, questions? Okay, so we've imported a bunch of stuff from disk. Really easy to do, and a lot of times that's what you're going to be doing. But next, in the next code chunk number 18, let's go ahead and import some online data because there's lots and lots of online data. I keep fewer and fewer spatial data on my laptop these days because so much of it is online, unless I'm doing something with it and I want to save a local copy. So in code chunk number 18, we're going to use the ArcGIS layers function package. Now, before we proceed, though, I think this will be illustrative, right? So we want to import the watersheds. And I told you the hardest part about importing cloud data is sometimes it's just finding the URL, right? And again, this is a URL to the feature layer, right? Which in this case, ArcGIS. So you have here above code chunk number 18, the URL. I'm just going to throw this into my browser tab up here. And what we're seeing here is, it's an ArcGIS page. It's a couple things to note here. First of all, if you look at the URL, it's waterboards.ca.gov. It's not arcgis.com. So this is clearly an Esri page, but this means this is the California Water Boards. They have their own ArcGIS enterprise. So it's kind of like ArcGIS Online, but it's on their server on their URL. So that's just kind of a factoid. They have shared this layer. I don't need like a password or anything like that. But this is not the URL that we're going to use, right? This is the URL that kind of describes the data, which is very, very helpful. But what we're looking for is going to be a URL that goes to the feature layer. And if you look down on this page at the bottom here, you'll see URL. And I can just scroll over and make sure it ends with feature server. And that's the URL that I'm going to use in my code, right? So you can copy that to the clipboard. The other thing that we note here is that this feature layer, some feature server, there's actually 6 layers that it's got available, right? Sometimes it's one and only one, but here, there's something called hydrologic region, hydrologic unit, and so on and so forth. You have to read this dense text at the top to kind of figure out what those different layers are. But we're going to get the smallest layer, which is it's called planning watershed, right? So those are the tiny little basins, which might be like a creek or a stream or something like that. And then they aggregate up into the larger hydrological units. All right. So back to Posit Cloud and back to code chunk number 18. And that's what we see. I'm going to run code chunk number 18. I'm not going to run it all at once. I'm going to go through it line by line so you can kind of see what it's doing. So in code chunk, first we load the ArcGIS layers, and then we're defining the URL. And then next we're using arc open, and we're putting that URL into there. And if we see below what it's returning, again, it's information about that feature server. So again, this is it's like an open phone line, but we haven't really brought anything yet. In the next one, we're using the list items function from ArcGIS layers, and this is showing us again those 6 layers that are available from this feature layer server. And we see that the one that we want, the planning watersheds, is number 5, right? So the ID number is number 5. So that's what we're going to use in below that. We're using ArcGIS layers, the get layer function, and we're assigning that to an object which is named incorrectly. And then now here's the thing though. You might see underneath it where we actually bring the data in, it's commented it out. And that's because there's like over 7,000 of these little baby watersheds in the whole state. And if you can try to uncomment it, but I'm a little bit worried on Posit Cloud. You only get 1 gig of RAM and then it crashes. So I've got those commented out. It's not massive data. But if you run the last line in code chunk number 18, I saved, I printed it out on my laptop and I saved the PNG. You can see all the little baby watersheds, right? We don't need all these little watersheds, right? We're only interested in the park, right? So what we're going to do here, we could bring them all in and then do a spatial filter, just like we did before with the intersects function. But we're going to take advantage of the ability to let the server do that filtering for us, right? So that come down to code chunk number 19, and that's what we're going to do here. We're going to get some data from the cloud, from the California Water Board's ArcGIS Enterprise server, which they're very nice to provide for us. But we're going to pass a geome and ask it to only give us the polygons that intersect that geome. So in code chunk number 19, I'll just go ahead and run the whole thing. You see, it's pretty fast, right? It only took like well less than a second because I'm not bringing down 7,000 polygons. I'm only bringing down, how many am I bringing down? I'm bringing down 175 polygons and then plotting them. All right. So that's a handy thing you can do, right? You can, when you're getting data from online sources, you can provide um, a spatial filter or an attribute filter or both, right? So only get the data that you really need. All right. Yeah, so and again, we're using ArcGIS here. So Krata is another data platform that a lot of government entities are using. It's open source. But it has a similar kind of thing. There's a function you can use to get data, and you can pass a spatial or a attribute query. Okay, any questions? All right, because we're running short on time, I'm gonna let you do the. Uh-huh.
There is one question, Andy. So somebody mentioned that they missed it, but there's a buffer around the bounds. Is that a part of the filter? Is that just a previous layer?
Oh, excellent question. Well, it's because if we look closely, what we're passing for the filter geome is actually the bounding box of the park, right? That's what it wants. And that's easy for a server to process, right? It's just like, does it fall within this box, right? That's a lot easier than saying, does it intersect this squishy little polygon? Um, and then my guess is that, so, the bounding box of the park, it's a little bit bigger than the park boundaries. So that's why we're getting some stuff on the corners. Uh, it's probably also returning anything that intersects, any polygon that intersects that bounding box, um, rather than, contained fully within. There might be another argument we could pass to say we only want things that are fully within that bounding box, but intersection is probably pretty good. If we did want to only get if we wanted to reduce this further and only get the polygons that are fully within the park, we could, now that we have it locally, we could do that with that ST intersections. And again, we would probably want to use something like contains, but then you have to also look carefully at the edge cases, because I'm sure the park boundary does cut through some of the watersheds there. You can also do you could also like slice it, I think, or mask it. Good question.
Yeah, good question. Just like most things, it's always better to measure twice, cut once. So taking in a little more data than you need is going to be better than cutting out too much and then having to make
Yeah,
a new query.
that's a good point. We see the same kind of thing with raster data too, right? Because raster data, it's often in really, really large rasters, or, like they tiled it up and you get far more than you need. And usually like getting just what you need, it's often it's a two-step process. It's a quick and easy and fast to get, to limit it to a box. And then within that box, then you can like mask it a little bit more locally. Okay, excellent. All right, I'm gonna, uh-huh. Okay, any other questions? I know this is going kind of quick, and I kind of apologize for that. It's only 2 hours, doesn't last very long. Okay, I'm going to go back to the slides, and um, and then we'll come back and we'll do another exercise here. We'll see how far we can get. Okay, so I'm back at the slide deck now, and something else that you'll often encounter in working with spatial data are problems that come up. So there are some functions that you can use to deal with geometry problems. They're not the only kind of problems. Um, but sometimes, you get a spatial object where there is no geometry. There's a row for the feature, but it's missing a value in that geometry column, right? So you need to drop those because most of the functions that plot them or analyze them, they will complain if you're giving it a feature that has no geometry, as they should. So tidyr has a drop NA function that you can use and just pass it the geometry column, and any row where that column is NA or missing will get removed from the results, right? So that's a general um, function to remove NA values. I've had cases where I've downloaded some open source. I'll just have to say it was an open source GeoJSON file. I don't know who made it, but some of the polygons had Z values and some of them didn't. And it took me a really long time to figure that out, like what was causing it. But if you do need to, you can use this st_zm function, and that'll drop all of your Z values or M dimensions from your feature geometry. I think M is for time, if I'm not mistaken. But that will, and a lot of times you'll get a shape file or something, and it has Z values, but they're all zero. So like, what's the point of keeping them? So you can use that function to kind of clean up or fix your data. And then there are those other kind of geometric topology errors, like the slivers, or something is like looping over itself. I don't fully understand all those. But ST is valid. We'll check to see if your geometry has problems like that, those kind of geometry problems. And then ST make valid will fix many of them. May not fix everything, but it'll fix a lot of them. Okay. All right, so these are some utility functions which come in handy when you need them. Okay, next, let's talk about geoprocessing. So for this, I'm going to jump to a slightly different slide deck because I haven't like brought it in yet. But geoprocessing functions are part parcel of what we do with spatial data, wherever you're using it. And in general, this is a pretty broad term. It seems to be getting broader every decade. It covers more things. So, but I'm using it here as describing the functions that are doing something with the geometry. They're analyzing the geometry, they're altering the geometry, they're using the geometry to compute something or to save something. And there's kind of three families of functions that do this. There's a set of functions that return geometric measurements, such as area and length or perimeter, that kind of stuff. So we're going to see some of those. There are other functions that will actually create new geometries, right, from existing geometries, right? That's going to be your buffers and your clips and your intersections, right? So there's a set of those. And then there's another set of functions which will test for spatial relationships. Are they touching? Are they intersecting? Are they within 1 kilometer? Are they contained? And so forth. And these functions come in when we're doing spatial queries or spatial joins, where you're interested in the spatial relationship between two features. So again, so then you can select them or you can join them, which means taking the columns of this one and putting them over there. Okay. So SF has all the functions that you need for this, which is nice. You don't have to get something else for that. An important thing though is like all of the functions that do this, it's really better to give them, they work with the map units, right? So, and because of that, then it's generally best practice if the layers that you're feeding these various geoprocessing functions should be projected data. It's not to say they won't work with decimal degrees, but there's a black box of what's going on under the hood there. Okay, so let's look at some of the functions from SF that compute geometric values. So area, length, and distance. Those are the three that I know of. Can't think of what else you might compute with two-dimensional data. But one of the nice thing about these functions is that they'll return the area and they'll return the length, but they return it using as a units class from the units package. So because a lot of times you'll see a number, it's like, well, it's a big number. Is that like meters or feet? It's like, how am I supposed to know? And unless you're pretty familiar with the coordinate reference system that you're working with, you might not know. But these functions, they will read the coordinate reference system and they'll see that the map units are meters or feet, and they will return those values in those units, but also tell you what those are. Okay, and we're going to see that here in a second. We're going to see this in the next exercise coming up. So I'm gonna go past this. Okay, likewise, this is an example that we're gonna see in the next exercise. Pass this. Okay, well, that was quick. All right, so let's go back to our Posit Cloud and open up the next exercise called Exercise 2, Geoprocessing QMD. So go back to Posit Cloud, wake it up if you need to, and click on Exercise 2. Now I'm going to go ahead and give myself kind of a clean slate because these notebooks should be fully self-contained. Oh, before I close exercise 1, go ahead and, if you haven't already, click the render button on the first exercise. So it's that little button up at the toolbar. And what this is going to do, when you render a markdown document, it's going to go through the markdown document, and every code chunk that's there, whether you ran it or not yourself, it's going to run it. And then it's going to save the output as an HTML file, right? So for me, it popped up in a new browser tab. If you haven't done this before, it might say that you might see a little note that pop-ups are blocked. on your browser. So go up to your browser toolbar, and it's either on this side or that side. There's a little button where you can give it permission. You can give this website, posit.cloud, permissions to open up pop-up windows, and then click it and then do it again, and it should come up. All right. But this is the HTML file that you get when you render a Quarto Markdown document. And you'll also note in your files pane, you might have to refresh it, you see that HTML file is there. So if you want to download this HTML file and keep it for your records, you can just select the HTML file. You probably need to select the folder that contains all the images and stuff that's part of it in your RStudio files pane, and then download it from the cogwheel. You click the cogwheel and click export, and it'll download it to your laptop. Or you can leave it here and just come back to it on Posit Cloud if you ever want to look at it. All right. So, but let's go to exercise 2. And to give myself a clean slate, I'm going to go to the Run menu, and I'm going to click Restart R and Clear Output. All right, so when you're ready to jump into exercise 2, I would suggest that you go to the Run menu, the Run button, click the little drop down there, and then Restart R and Clear Output. So if there is any output that's been rendered in this document, it'll go away, and it's going to restart your R session. And then for good measure, I'm going to click the little broom icon to clear out my console. I guess I could close my console as well. And now we're good to go. We've got a fresh slate. I can see there's nothing in my environment. No objects have been saved. So clicking code chunk number 1 in exercise 2 and run those library statements. So we're just loading up some packages using the conflicted, because we're using dplyr here. So dplyr has a couple potential name clashes with other packages. So that's what the conflicted statement is doing down there. And then code chunk number 2. In code chunk number 2, we're importing the park boundary. We've seen that before. But what we're doing in this notebook is whenever we import something, because they're going to be in different coordinate reference systems, at the same time we import a layer, we're going to simultaneously project it into UTM 11 North NAD 83, right? So that's one of these CRSs. And there's a variable that we're creating with the EPSG code for that CRS. All right, so we've imported the park boundary in code chunk number 2. So code chunk number 3, and one of the reasons we are converting it to UTM 11 North is because that is a projected coordinate reference system, and the units are meters. The map units are meters. So now in code chunk number 3, we can simply pipe in the Yosemite boundary into ST area, and that will compute the area of the polygon. Now in this case, there's only one polygon, so we're only going to get one number. But if this was a layer that had a bunch of polygons, we would get a vector of area values. Okay, very good. So, and as you can see, when we look at the results, that we're getting, it's a big old number, but at least we know that this is meters squared, right? So I still can't really wrap my head around that big number. But because it's saved as a units object in code chunk number 4, we can convert it to miles squared, right? So we're using the set units function, which is actually from the units package. It's not from SF, but we're taking that Yosi area value and we're telling it to change the units to miles squared. And this is a little bit easier for me to, digest, right? So it's 1,165 miles squared. Big place, big place. Okay. So next thing we're going to do in code chunk number 5 is compute the is to bring in the watershed boundaries. Now we already did that from ArcGIS Online, but the watershed boundaries are also saved in a geo package. So inside the data folder, there's a geo package. So what is a geo package? a geo package, it's a lot like it's a bit like a geo database in the sense that fundamentally it's a database format that can store different kinds of layers. It's different than a file geodatabase in that it's a single file that in this case has an extension JPKG, whereas a geodatabase is a directory or folder, right? But it's a well-known database format for spatial data, and I think in QGIS it's kind of the default container or storage device for QGIS projects when you create a QGIS project. So in code chunk number 5, we are importing a layer from a geo package and uh, and plotting it. All right. So what we can see here are the results. I don't know. These are the Huck 8. Actually, these might be the Huck 12 watersheds. Anyway, they're basins. They're like the little watershed basins. So next, we want to compute the area of each of those watersheds. And not only that, we want to add those values in the data frame, right? So right now, if we look at the watershed, so if we look at the columns that we have, we see a bunch of columns, but we don't see like shape area. So we don't have a column for the area. So if you are working with areas, it's generally a good idea to compute it or recompute it anyway. We've had more than one project where the area of the parcel that was in the attribute table was wrong, right? Something happened and it didn't get updated. So in code chunk number 6, go ahead and run code chunk number 6, and basically we are adding a column for the area of these watersheds. And you can see how we're doing that, right? We're using mutate from dplyr, because again, these are simple SF data frames are still data frames, so we can use mutate, and we're populating it with the area values, right, that we create first. And if I scroll over, and I can see, yep, there it is, area underscore M2. So that's the area, and it's still a units object. Okay, let's keep going. I'm going to skip the next challenge. Let's come down to code chunk number 8. And here we're going to import the roads, which are saved in a file geo database, right? So here we're bringing in I think this might be the first time we're bringing in a layer from a file geo database from the Esri world. But as you can see, it's a single command, and we're simultaneously projecting it. I don't even know what projection system it's in. Doesn't really matter because we can quickly reproject it to UTM 11 North, which is the projection system we're using for all the layers in this exercise. And then also use the select function to select just six or so of the columns, because I think this is one of those layers that the Park Service or whatever contractor put it together. There's like 38 columns. So these are just roads. We don't need to know all the details. So we can use the select function when we're bringing it in to just get the columns that are going to be useful to us. And then in code chunk number 9, we're going to compute the length of all the roads. And again, we're using mutate, so we save that into back to the feature layer. Okay, any questions? All right, I'm going to skip the next challenge and come down to code chunk number 11, where we're going to import the campgrounds. So run code chunk number 11, and this should all be very familiar now, right? We're using stread. We're bringing in the points of interest layer, and then we're piping it to transform it. We're piping it again to pull out just the campgrounds, and then we're using the select. So here you can see that all of those data wrangling methods that we learned 2 weeks ago work out of the box with no edits to simple feature layers. So that's why SF and the tidyverse to make a really good combination. And then we also have a geodatabase for the cell towers. There's a small number of cell towers in the park. Okay, so that's code chunk number 11. Code chunk number 12 is a plotting challenge. I'm going to skip over that because we just have a few minutes left. But let's go ahead and finish up here by computing the distances between the campgrounds and the cell towers, for example. So code chunk number 13, we're using st distance, right? So st underscore distance. And this is a function that computes distance. Now, if you only pass it one SF object, in this case, we're passing it the campgrounds. And there's 12 campgrounds. Sorry, there's 15 campgrounds in the park. Campgrounds are not campsites. There's like thousands of campsites, but there's only like 15 like official campgrounds in Yosemite. And we're passing it only those campgrounds to st distance. So it's going to basically do pairwise. It's going to compute a matrix, which is kind of like the pairwise distance. And again, in map units. So this is a UTM layer. So these numbers that we're looking at here, that's the distance between, campground number 1 and campground number 2 in meters, right? May or may not be helpful, but what we get back is a matrix, right? That's if you pass st distance a single SF layer. If you pass it 2 layers, so in code chunk number 14, look at code chunk number 14. Here, we're passing the st distance, the point layer for the campgrounds, and then the point layers for the cell towers. And here, it's going to compute, you can see the results is we have a 15 by 5 matrix, right? So now it's doing pairwise comparisons, right? So for every feature in the first argument, it's computing the distance to every feature in the second argument. Okay? And then finally, we are, if you really just want to know, okay, all I want to know is what is the closest campground what is the closest cell tower to every campground? Then that's what we're doing in code chunk number 15, which is one way you can do that is to grab the first column of the matrix where we did that pairwise comparison, and that'll tell you what number it is, or so that'll get it for one column, for one campground, or you can use that apply statement to get it for all of them. Now, this actually still isn't very good, is it? Right? So we would probably want to use another function from the SF package, which would be, return the nearest, right? And there is a function which isn't just going to compute under the hood, it's going to compute the distances, but what it will return is the nearest. I think it's called SF, it's called ST nearest. Yep, nearest feature, right? Nearest points. So we'll stop there because we run out of time. But you could keep going with that, right? So maybe the challenge for you would be to, for every campground, all 15 of them, find the ID number or the name of the closest cell tower. All right, well, we didn't get through everything, but we got hopefully what we got through was solid, and that you picked up some of the fundamental terms. There's another the next section we could cover would be spatial queries, which is similar, kind of like ST nearest neighbor is a spatial query. It's fundamental, it's like selecting objects, features based on their spatial relationship. So I'm going to stop talking and pause if people have any questions. If not, enjoy the rest of your Friday. Feel free to sign up for office hours if you like to chat about any of this stuff. Myself, Genoa, the rest of my team, we're fundamentally spatial data nerds, so we enjoy talking about all this stuff. So this was a start, and hopefully it'll keep going. So. Thanks.